Okay, so we're going to keep moving on through chapter 6. This is lesson 3. It's called rotation. So we'll be turning things around the x-axis or the y-axis or about the origin, that kind of thing. So we have here some vocab on slide 1. A figure has rotational symmetry if it can be rotated or turned less than 360 degrees about its center so that the figure looks exactly as it does on the original position. So you can rotate it maybe 90 or 180 degrees so that it lands upon itself. So this one we would rotate 90 degrees each time and it would land on itself and it would have a degree of 4. So can we turn this figure less than 360 degrees and it still look exactly the same time? Yeah, 90 degrees. How many times? 4. Just answered that question without reading the box first. So we're going to practice that with a couple of some figures. The degree measure of an angle through which the figure is rotated is called the angle of rotation. So when you rotate something all the way in a circle, that's 360 degrees. Find the first angle of rotation of the first logo by dividing 360 degrees by the total number of times matched. So this, can we rotate it less than all the way around so that it lands on itself? And that's yes if we rotate it, not here because it would be upside down, but all the way here, if we flipped it upside down, that we would have rotational symmetry. So we would take 360 degrees divided by 2. It has rotational symmetry, and that's 180 degrees, and it's because it has a degree of 2. The angle of rotation is 180 degrees because we have to rotate it twice. So that's what you'll be writing on your homework. This butterfly, we can't turn it until we turn it all the way around, and so it does not have rotational symmetry. This snowflake, we could turn it here, we could turn it here, so that's once, twice, 3 times, 4 times, 5 times, 6 times before it lands on itself. So 360 degrees divided by that 6 rotations is 36 divided by 6 is 60. So 60 degrees is our angle of rotation. This Olympic medal, we can't turn that unless we turn it all the way around. So this does not have rotational symmetry. So these are the 2 numbers that you will write on your homework. When it asks for the angle of rotation or rotational symmetry, you put 2 and its angle of rotation here. Some more vocab words, slide 3. A rotation is a different type of transformation. It's a transformation in which a figure is rotated or turned about a fixed point. The center of rotation is the fixed point at which something is rotated. A rotation does not change the size or shape of the figure, so they're congruent. So the preimage and image are congruent. So a little side note here. Rotations can be described in degrees and direction. For example, 90 degrees clockwise, so if we started something here and we turned it 90 degrees, if we're thinking about it in a coordinate plane, it would come down to this coordinate plane, and that would be clockwise. We're following a clock. But that's the same as going 90, 180, 270 this way. So they're synonyms, just 2 different ways of looking at something. Okay, so it says triangle LMN with these vertices represents a desk in Jackson's bedroom. He wants to rotate the desk counterclockwise 180 degrees about vertex L. So we need to graph the figure in its image. So L is at 5, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. There's our L. M is at 5, 7. 1, 2. 5, 7. And N is at 8, 7. So here's 5, 6, 7, 8, 7. So there's N. So he has a triangular shaped desk. Now it says he wants to rotate the desk counterclockwise 180. So here would be once, here would be, or that would be 90, and then we're going to rotate it again. So if we think about point L being fixed there, if M came down here, that would be our 90 degree. But we want it to come all the way down here. So I'm just going to redraw this down here. So it gets down 2 boxes, 2 distance here. I'm going to put this in my purple. L stays the same. L and L prime happen to be the same. So then M becomes this M prime. And I'm just going to look here. N is 3 away from N. So I'm going to just draw that 3 away from N here. There's no nice like formula for these ones when they're about a fixed point. You just kind of have to think about it. So here would have been 90 degrees. Another box is another 90, so 180. So L is on the same spot, so still 5,4. M, though, now is at 5,2. And N is at 2,2. So writing our new coordinates for our image and pre-image. Pre-image, image. Oh, I forgot the prime on N. N prime. There we go. Okay, so slide 4. Similar, we're going to rotate it about a fixed point. Rectangle ABCD has these vertices. Negative 7, 4. 1, 2, 3, 4, 5, 6, 7. And then up 4. 1, 2, 3, 4. So there's my A. B is negative 7, 1. C is negative 2, 1. And D is negative 2, 4. Okay, if I attach that, this is a bed in Jackson's room. So he's moving his desk and his bed. We want to graph the figure and its image after a clockwise rotation of 90 degrees about vertex C. So this stays the same. So all of this needs to come down once. So if I think about D being 3 away from C, it now needs to be 3 away from C. 1, 2, 3, D prime. C and C prime are the same. Now if I think about A being 1, 2, 3, 4, 5 boxes away from D, I could do that again. 1, 2, 3, 4, 5. That was A prime. And then B prime would have to line up. So he's going to rotate his bed 90 degrees about C. And then we would write those vertices. D is now 1, 1. C stayed the same. B went to negative 2, 1, 2, 3, 4, 5, 6. And A is 1, 6. So there's not really a nice way to tell you, when we've talked about just flipping one thing or the other. It's not nice when they're about a fixed point. But don't worry too much because there are some nice rules for rotating about the origin. So on slide 5, it says about the origin here. This is important. These are origin. These were about a point. Origins are a little bit easier because they have a rule every time. A rotation is a transformation about a fixed point. Each point of the original figure and its image are the same distance from the center of rotation. So here we have something about a 90 degrees rotation, about the origin. And it gives us a rule. So the 90 degrees about the origin, x, y becomes, we flip the y and the x becomes negative. The 180 degrees, we get to flip the signs on both of them. 270, we flip the y and x, and the y becomes negative. So if you think about it, the 90 goes to the right, so your x's have to switch because it flips to the right. In 180, the x flips now, and then now the y flips, so both of them change. And here, moving, this is the x. This would make the x positive again, and here we get to the y, so we have some y switching. So it's just one of those things that we're going to have to kind of work with. Now all of these are clockwise, but counterclockwise are the same thing. So a 90 degree counterclockwise is the same as a 270 degree clockwise. 180 are the same in both cases. 270 counter is the same as a 90 clockwise. So if we can remember these, then we can draw them, maybe good things to put on our foldable. These would be good things to remember. So slide 6. It says triangle DEF has these vertices, so graphing these, 1, 2, 3, 4, negative 4, 1, 2, 3, 4. E is negative 1, 2, and F is negative 3, 1. Okay, it says we're going to graph the figure and its image after a clockwise rotation of 90 degrees. So if I go back over to slide 5, clockwise rotation goes from xy to y negative x. So all of the y's get put in the x position. So 4 is in the y there, so it becomes the x here. 2 becomes the x. 1 becomes the x. Why I have a g, I don't know. And then it says, now put the x in the y spot, but make them negative. So the x was -4, so we need to put it in the y spot and make it negative, so +4. And a 1. And a 3. So switching the spot and making them positive. So 4, 4, 1, 2, 3, 4, 1, 2, 3, 4. That is our D prime. E prime is 2, 2, 1. And F prime is 1, 3. 1, 1, 2, 3. So we took this whole thing and we rotated it to this quadrant, which is our 90 degrees, and then everything had to follow suit. So the D came to the top, the F below it, and the E down below. So that was a 90 degrees clockwise, could also be a 270 degrees counterclockwise. Okay, so slide 7, one more to practice with. Quadrilateral MNPQ, so 4 of them, has these vertices. 2, 5, 2, 1, 2, 3, 4, 5, that's M. N is 6, 4, 3, 4, 5, 6, 1, 2, 3, 4, 6, 1, P, Q, 2, 1, 2, 1. Okay. Kind of looks like a trapezoid. It would be. These are parallel. Okay, so then we have, we can rotate it 270 degrees about the origin. So that says from slide 5, it's talking about counterclockwise 270 about the origin. Counterclockwise of 270 is the same as a clockwise of 90. So that's the same rule as before. XY becomes Y negative X. So all of the Y's from the original need to go in the X spot. So M becomes 5, 4 goes to X, 1, and 1. Those Y's became X's. Now the X's have to go to the Y spot and become negative. So 2 becomes -2, 6 becomes -6, 6 becomes -6 again, and 2 becomes -2. Now we can graph them. So 5, -2, 1, 2, 3, 4, 5, -2, 1, 2. That's M. Because we're rotating this whole thing in 90 degrees. And then N is 4, -6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. P, 1, -6. And Q, 1, -2. So when they're about the origin, so this whole thing flips 90 degrees, one quadrant, or you can think of it as 1, 2, 3 quadrants this way, so that's that 270 degrees counterclockwise. And everything needed to turn and then shift down, essentially, but we don't always know how much to shift it down, and that's where these rules come in handy. So keep those rules close, maybe write them on your foldable, so when you get your chance to take your rotations out, symbols, and model it, I would write those rules in here. All right, that's all I have for you. Nice picture of a crop rotation for farmers. It's a joke, it's a pun, because every few years you should rotate your crops from beans to corn to something else. So here's a picture of a crop rotation. Have a great day.